Hello and welcome to another Commodore 64 assembly programming video. Okay, so let's do a quick recap where we've got to. So last week we did sprites, or basic sprites. The link to that video is up in the corner. And then the week before we did beginning kick assembler and doing tricks with screen memory. So what are we going to do today? Today we are going to do interrupts. Interrupts are bits of code that get executed automatically by the system when a certain event happens. Now, a lot of this is built in, so what we'd like to do in this is actually put our own custom interrupts in so that it can execute some code when we want it to, and it's our custom code as well. So, the first thing about interrupts is that interrupts happen automatically. It's all built into the kernel, mostly when you have a CIA event, like the keyboard being pressed, something coming in on the tape port, anything like that. We're not really going to be using those as such. What we're going to do today is use Raster line interrupts. Now, raster line interrupts are when the raster bar that draws the picture on the screen, I think in PAL it's 25 times a second, I believe. Could be 60, I'm really not sure, but what we're going to do is we are going to trigger some code to happen when the raster bar hits a certain point on the screen. Now, what that is useful for particularly is keeping things smooth on the screen so that a change gets drawn before the raster bar actually draws it, and also playing music as well, because most SIDs are designed to be played once per raster cycle. So a bit of the SID is played, then it's carried on when the next raster cycle happens, and that's how the speed is governed of the SID. Okay, so how do we go about this? Okay, well, what I've done, I've added some new constants into our constants file. I appreciate a couple of these may already be in the Vic2 constants under a different name, but I thought for the benefits of this video, I would separate them out. Okay, so we've got the interrupt register. That's where we can control what interrupts, what events generate interrupts. Okay, so we've got the raster and sprite interrupt register here as well. That's for doing raster and sprite specific interrupts like collisions or raster line, etc. Okay, and we've also got here raster line MSB and raster line. Okay, so the raster line is greater than 255. Okay, so it goes up to 320 odd, I believe. So we can't store that in one memory address because it's only 8-bit and only has a maximum of 255. So we need another bit, which is the 9th bit, or as they call it, the 8th bit, because the first bit is the 0th bit. Okay, so this address here, bit 0, is the most significant byte of the raster address, so it can go up to higher than 255. So if it got to 256, for example, this would have 0, and this would have at least the value 1 in it. Okay. If it's under, this would have the value 0 as the bit 0 in the address, and this would have whatever the value under 255 is. Okay. What we've also got here, we've got the interrupt execution, high and low. Okay, what this is 2 pieces of memory, because it's storing a 16-bit number, which is a memory address, and that is when an interrupt happens, any interrupt, where does it have to branch to run the code for that interrupt. So because it's a 16-bit address, we need to store it in 2 bytes of memory. This last one is our interrupt status register. So when we run the code, that the interrupt causes, we have to set some bits in here that acknowledge that we've handled that interrupt. Okay, and this address here is where all the system interrupt code is that's built into the kernel, which is like handling key presses, joysticks and everything else like that, because we may want to run that after we run our custom code. Okay, otherwise it won't be able to handle joystick movements, key presses, etc, etc. Okay, so let's set ourselves some interrupts. So what we'd like to do is we would like to disable the CIA interrupts, okay, because they are far too often and we can't really predict when they're going to happen. We want to have interrupts run when the raster bar reaches a certain point. Okay, so let's go to today's code. Okay, so what we're going to do, we are going to import our source. Our constants there. Okay. We're going to start our program at 3000, and the reason for that will become clear in a bit, and then we will call our first function IRQ init, so interrupt request init. Okay, and what I'd like to do is I would like some basic that will run our program and start it here. Okay, so we do basic up start 2 at IRQ init. Okay, so what this program will do now, okay, it will go to this address using a basic syscall, which is generated here, and run, and there's nothing to run obviously at the moment. So always like to down the bottom put a RTS, so that will return back to basic whenever it's done. So this will actually do nothing at the moment, it will just go back into basic. Okay, right, so we want to set some interrupts up, or an interrupt up when the raster bar reaches a certain level. Okay, so if we're messing around with interrupts and we want to customize them, the first thing we need to do is run this command, SEI, and that will suspend all interrupts while we're doing this. Okay, so while we're customizing which interrupts trigger things, we need to suspend the interrupts. Okay, what I'm going to do now is I'm going to load into the accumulator this number here, 7F. Okay, and if I look on the calculator, we'll see exactly what that's doing. So we'll go into hexadecimal mode, we will do 7F, and if we look at the binary here, you see what this is doing is disabling the 7th or the 8th bit, bit 7, and that's bit 0, so it's disabling bit 7. Okay, and that is for CIA interrupts. Okay, so what this is doing is if we store this number into the interrupt, typo there, the interrupt register. Okay, in fact, tell you what I'm going to do. I'm going to do some binary here, so we know 1, 2, 3, 4, 6, 7. We know what it's doing. Okay, so it's turning this bit off and keeping all the other bits on, which there will be, and into the interrupt register. Now, if we look at the interrupt register, it's DC0D. There's a very, very useful website which I will link to in the description, which is the memory map of the Commodore 64. So if we look at that address, DC0D, and we'll scroll down to it, okay, we can see it's the interrupt control register and status register, and it tells us what all the bits are. So we're disabling this bit here, which is the timer A underflow. Okay, so it won't trigger an interrupt when there's a CIA timer underflow, because we don't want an interrupt then. We only want an interrupt when the raster bar hits a certain raster line. Okay, so we've disabled CIA interrupts there. Okay, now what we want to do is we want to enable raster interrupts. Now, if we look here, we've got raster sprite int reg, which is raster's sprites interrupt register is D01A, and if we go back to here on our memory map, okay, that's the interrupt control register bits there. So we want to turn on bit 0, which is enabling the raster interrupts. Okay. So this is a register we want to use. So what we're going to do, we don't know what the other bits are, and we want to leave them as they are in that register. So we will do a trick here using an OR. It's ORA, which is OR the accumulator. So we're loading the contents of this register into the accumulator, and we're going to OR that with the number 1, or in binary, to show you what I mean. Okay, we basically are ignoring the other bits because this is an OR function, a logical OR, and whatever they are, and we will just make sure that bit 1 is turned on. So the OR function is a function to turn selected bits on and off. So if you load a number into the accumulator and you OR it, it will turn on whatever bits are in number 1 and leave the others as they are. So we've OR'd this number, the value of this register, and now we want to store it back in the register. Okay, like that. So that should now have raster interrupts enabled. There's one more thing we want to do. There's another register here called, I've done it as raster line, and there's raster line MSB, which we discuss. It's D012. If we go onto our memory map, okay, so when you read from it, it gives you the current raster line, where it's at. If you write to it, that is the raster line to generate the interrupt. And the same is with a bit 7 on D011. Okay, so that's the 8th bit of this number. Okay, as I said before, because it needs to go higher than 255. Okay, so we want to write to this and tell it what raster line we want to generate interrupts at. So I would like interrupts at the topmost raster line, which is line 0. So the way we do that is we need to make sure 0 is in D012, which is the 8-bit part of the address, and we need to make sure 0 is in the extra bit that's in D011, so that the entire number is 0. So our raster line will be generated at 0. Okay, so the way we do this is we want to clear the bit on the register that has the overflow bit on it, because the other bits are used for other things. We don't want to touch those. So we want to literally do the opposite of this function. We want to turn that bit off. So the way we do that is we load it in. Let's get it from here. This address here, and we want to turn off the raster bit there. Okay, and we want to do it in a similar way to this. We are going to use AND. Okay. and it's bit 7, which is this bit here. So the way to turn a bit off is to, let's use binary, use a 0 for the bit you want to turn off, and everything else is a 1. Okay, so whatever these bits are in that address will be unaffected. It will just make sure this is 0 at the end of it. Okay, and we will store that back. Okay, and the last thing we want to do is clear the 8-bit part of this Raster line register as well, which is, so we can just set that to 0 because the Raster line uses the entire byte of the address. So we will put a 0 in, and we will store it in this address here, D012 Raster line. Okay, no, autocomplete, and it's done it again. Okay, so we'll store that in Raster line. So now what we have is we've disabled CIA interrupts. Okay, we've enabled Raster interrupts, and we've selected Raster line 0 using these two addresses as when the Raster interrupt is occurred at Raster line 0. So, what do we want this to do? Okay, so what we should do is write a little bit of code, and let's write a function. So we're going to call it IRQ. Okay, so here is where the code for our interrupt will go, which will run every single time the Raster line hits line 0. Okay, so before we actually write that code, we need to do a couple more things in here. Because we want it to run this particular code at this point here, we need to store that in the interrupt execution address registers. Okay, and as I showed you before, it's these here. There's 2 of them because it's a 16-bit number, because it's a 16-bit address. So let's store that in there now. So we will load, and this is the clever part, it's a hash because we're not loading the contents of a memory address, we're loading a number. And if we use the less than sign, okay, so that will be the address of this point here, and it will be the least significant byte, which is what this less than sign does. Okay, and we're going to store that into our interrupt execution. Okay, so we're going to store that into this address here, and then we need to store the high byte part of this 16-bit number here. So you've guessed it right, we use the greater than sign, and we'll store that in interrupt press execution high. So I believe that's all we need to do here for now. So if you see here, we disabled the interrupts while we set all this up. We need to re-enable them now. So we use the CLI command. Okay. Now let's do the function code for our actual IRQ. I'm probably not going to do very much here, just as a demo here at the moment, because we're going to add some stuff later on. Let's do some basic practice stuff, or best practice stuff. Okay, so because this code will run every time the Raster bar hits line 0, okay, it will just, the program will branch away from whatever's running, run it, and then come back to it. So if we're doing stuff in here that involves the accumulator, X register and Y register, it will overwrite what the accumulator, X register and Y register are currently containing in respect of the code that's running in the background. Okay, so if I'm writing a program that's pulling values into the accumulator and storing them somewhere like I did in the screen, and then it branches off at line 0, runs this code, does something to the accumulator, and then returns the accumulator values that the screen memory routine were running, will be lost. So we do not really want to lose that. So there's a nice feature in 6502 called the stack, which is a last in, first out part of memory that we can store things in. So what I'd like to do here, and what most people should do, is store the current accumulator X and Y registers into the stack, run our interrupt code, and then pull the values back out of the stack back into the registers so that it won't destroy what's happening in the actual main code. So we do that this way, okay? PHA will push the contents of accumulator onto the stack. We can't push the X and Y register onto the stack, but we've got a better way to do that. We transfer the X register contents into the accumulator, push that to the stack. Then we transfer the Y contents of the Y register into the accumulator and push that on the stack. Okay, and they can stay there while we do our interrupt code, and then we will do exactly the opposite, which will be down here. Okay, and what this does is it pulls them off, the values off the stack in the correct order, and puts them back into the correct registers. So the Y register was the last item to go onto the stack, so it's the first item to pull off. So the way we do that, we do PLA, which is pull the item off the top of the stack into the accumulator. We'll transfer that, the accumulator, to the Y register. Oh, I don't really like this autocorrect doing that. Okay, so the next one is the X register, so we pull the next item off the stack into the accumulator, and then we transfer. It's auto-corrected again, didn't it? And we transfer the accumulator to the X register. Space after it, that stops the autocorrect. So we've restored our X and Y register, so now we just need to do one more pull, which is the original accumulator value, and it goes back into the accumulator. So this basically is putting the X, Y and accumulator register values as they were before the interrupt started. Okay, so whatever we do in here with the accumulator and everything else will not affect the actual main program. Okay, so it's preserving the register values. So when you are doing an interrupt, there is one thing you must remember to do in your interrupt code, and that is acknowledge the interrupt. Okay, so we looked over here. There's an interrupt status register, which is D019. Okay, now if we look at that in our memory map, that's the interrupt status register. Okay, so the bit that will be set is bit 0. Okay, which is current raster line is equal to the raster line to generate the interrupt at. So when our raster line hits 0, okay, it will set bit 0 in this register. And what we need to do is we need to set this back to 0 once we've run our interrupt code, so that it's ready to generate the next interrupt. So it's called acknowledging the interrupt, basically. So let's go back to our code. Because it's the first bit in that register, it's very easy to do. Okay, all we have to do is decrease the value of that register by 1, because it's the value 1, because it's bit 0. Nice and easy. So we would just dec, which is decrease by 1, interrupt status. Okay, so what I'm going to do is I'm going to just put this into a separate, put a label on it. This is the acknowledgement. Okay, so what happens is the IRQ is, the interrupt is generated, the program jumps to here, we preserve the contents of the registers, we then run our code, which doesn't exist, and then we acknowledge the interrupt by resetting bit 0, and then we restore the contents of the registers so the program can continue running without any interruption. Okay, so the last thing I'd like to do on here, once it's run my custom interrupt code, which I haven't written yet, as I'd like it to then run the kernel code, which will react to key presses, joystick inputs, everything else like that. Okay, but the difference here is it's running every raster interrupt rather than every CIA interrupt. So that's quite easy. We've got this address here, which is syst_irq handler. All we do is, once we've acknowledged our interrupt, restored the contents, we do a jump to syst_irq handler. Because if we didn't do that, then our program would not react to key presses or joystick inputs or anything else like that. Once it's run that, it will return back to our program, which again doesn't exist. Well, this is our program right here. Let's save that and let's see what happens. I can guarantee not a lot will happen, but you may notice something slightly different. So let's build that and run. Let's see if it builds. It does. And there we go. It has run. And there's nothing different here at all. Okay. What is different is the flashing of the cursor. It's very slightly different because it's running the code for that every raster interrupt instead of every CIA interrupt. Right. So the next thing is, let's actually get this interrupt to do something. So, what should we get it to do? What happens on the Commodore 64 that more often than not will use raster timing to run? I'll tell you exactly what. It is playing a SID. Okay, so I happen to have downloaded a SID for this example. I downloaded it from the high voltage collection. There's thousands and thousands on there. This is one I particularly like. And the good thing about Kick Assembler is it's got a nice little SID importing utility. Let me show you how that works. So we do a variable here, and we'll call it music. And we use this function here, load SID, and it's cheese.syd, which is in the same folder, so it's here. See? Okay, so that loads the contents of this SID into this variable. Now, SIDs are self-contained programs. They've got their own memory start location and everything else like that. That's all built in, and if you want to change the portion of memory where the SID lives, you need to use a special utility to do that, which I will link to. So our SID's in here, but we actually want to play it. So what we need to do, we need to output the code for it. Now there's a nice built-in way to do that. So this asterisk equals is a memory location. So music dot location, and we'll call this segment music. We don't have to do that. I'll show you why we do that. Okay, so this memory address is the location of the variable music, which is the SID. So it could be this address is whatever the memory location is defined in this SID file. Okay, I don't know it. I do, but we don't. As a programmer, we don't know it until we put it in here. Now, what I need to do is I need to use another trick that comes with Kick Assembler. We now need to fill from this location onwards the actual code of the SID file. So it's music.size, which is the size of the code. That's what the fill function does, and that tells us how much we need to fill. And now we need to tell it what to fill, which is music.getData, and it's use an I because it will repeat until it's done. So basically our SID code will all be here in memory. Okay, I mean, I happen to know that this particular SID, the memory address for that is 1000, which is hence why I started our program at 3000. So our SID code will sit at 1000 before it hits our program code. So I know for a fact also that it won't overlap because it's less than 2000 bytes. So we've squeezed it all in nicely there. So our code for our SID music is in memory, but we've got no way of actually playing it. So let's look at how we're going to do that. Okay, there is some routines in our music, and we need to run these in order to get our SID to play. Okay, so what we need to do in order to get our SID music playing, there's a couple of things we need to do. A lot of SIDs have more than one song in them. You can have the level music or the intro music, or you can have some music when you die, some music that contains sound effects when you're shot, some end of level music. Okay, so most SIDs have more than one song in them. Obviously Cheese has one song, but it's song number 1. So once our program's initialized our custom interrupt here, what we'd like to do is initialize the SID. So we load accumulator, and it's a actual value rather than the contents of a memory address, and it's music start song -1, and then we jump to the subroutine, which is a go sub, and this is a memory address, music.init. So that will initialize our SID with song number 1. Okay, let's just double check that by running it. We can't do that. Our compiler has picked up a typo, and that'll be here. Location. Who's ever heard of one of those? Okay, again, it doesn't do anything, but it doesn't error out, which is what I wanted to do. Now, if we take a look at here, we can see when it's compiled, this unnamed segment, because I haven't named it, is the bulk of our program. And this is our music, so it's memory address 1000 to 1E51. So again, there's no overlap. I could have even started our program at 2000 if I was short on memory. Anyway, back to our program. Okay, so I want to play the music. So what I need to do here is in our interrupt, I want every Raster interrupt to play another bit of SID music, because that is the way the SID is set up to use Raster timing. So once we've done our preservation of the program registers, we're now going to jump to the subroutine, which is music.play. And that's it. Now, the good thing about interrupts is they will carry on running even when the main program has stopped. So if you notice here, once everything's done, it just does an RTS, which returns us back to basic. The interrupts will still run, okay, until we clear them. So let's have a look and see what this does. There we go. I hope you can hear that. It's now playing our SID music, and we're in basic. We can do whatever we like. See, there's our program listing, and we have some SID music playing. So every time the Raster bar hits up the top here, then it's playing a bit more of the SID. Okay, now, as I discovered a while ago, if I try and play a SID using the standard interrupts, the timing is completely wrong and it just sounds horrific. So I think you'll find most SIDs are designed to be played in Raster timing, so once every Raster redraw, which is essentially what we've done here. Okay, right, so let's recap. Okay, we've set our interrupts up, we've disabled CIA interrupts, we've enabled Raster interrupts, we've set the Raster interrupt to happen at line 0. Okay, and then we've pointed the interrupt execution register at our custom code address. So, and then we've CLI, which gets everything, which re-enables the interrupts because we disabled them there while we were programming them. So, we have some code here. All this does is initialize the SID music and then return us back to basic. So it just runs this once and leaves us back in basic, and the basic routines carry on. But in the background, every time the Raster bar hits bar 0, okay, or line 0 should I say, this code is run, which preserves the accumulators, plays the next part of the SID, and then acknowledges the interrupt and then restores the accumulators and then carries on to the sysIRQ handler for key presses. If I didn't do this, then when I was in basic there, I probably would not have been able to type anything out unless basic would override that, which I'm not sure and I don't want to try, but I did try it in a program before which was waiting for a key press in assembler, and it would not detect it until I put this in. Okay, right. Let's say now we want more than one IRQ. Okay, we want to do something when the Raster bar hits a different point in the screen, but we don't want to interrupt what we've got here. Okay, so ways we can demonstrate this is we can change the border color at a different point in the Raster bar. Okay, because when you're in basic, you can only have one border color. You can't really do stuff on the borders. Change the colors. Well, you can change them, but it changes the entire border. So let's see what happens when we do that with Raster interrupts. So, because I want more than one IRQ, I'm going to change this to IRQ1. Okay, so that means I'll have to change this as well because I still want it to go to IRQ1 when it hits Raster line 0. So the first thing I want to do is in my IRQ1 is I would like to play the SID, play its part of the SID, and then what I'd like to do is change the border color to green at Raster bar 0. So Let's have a look. I need to import all my colours, which are in Vic2 constants. So let's do that. Okay, we covered that in the last video. So we will load the accumulator with the value, not the address, of green. And we will store the accumulator in border colour. Yes, I know it's the American spelling. I've still not corrected my Vic2 constants. I've got duplicates in there, as some viewers have pointed out. Yeah, I will get round to tidying those up. Okay, so what is this going to do? Let's run it. So all it does is gives us a green border. It'll still play a nice SID piece for us. So yes, this gives us a nice green border. Why does it do that? Okay, so basically it's setting the border colour to green every time the raster bar hits line 0. Okay, so it's setting it to green every either 25 or 60 times a second, whatever it is. I can't remember. I really should. So how does that help us? We can do that in BASIC. We can set the border colour to green repeatedly. Okay, well, what I'd like to do now is write another IRQ. So what I'm going to do, I'm going to leave this code here underneath it. Okay, but what I'm going to do is jump to ACK. So when it has run this, it will jump straight into this anyway, so it doesn't matter what I put after it. So let's do our IRQ2. I want to do the same here. I want to preserve the registers. But in this IRQ, I want to store, let's copy this, I want to change the border colour. And I want to change the border colour to yellow. Okay, so at the moment you're probably thinking, well, that's never going to run, is it? Because the raster hits line 0, it runs what's in IRQ1, then it acknowledges it and then waits for the next interrupt when the raster hits 0 again and then runs again. Yes, you're quite right. So what we need to do is we need to configure on the fly a new way of triggering this, and I'd like to trigger this at a different point. So I want to trigger this at a different raster line. So I want IRQ to run at raster line 0, and I would like maybe 150, line 150, which is about halfway down the screen. I would like this to run. So how are we going to do that? Well, it's simple. The raster interrupt will occur when the raster bar line number is whatever we put into these registers here. So we need to change this on the fly. So at the moment, 0 is in there and the byte in the MSB register is 0. Byte 7 is 0. Okay, that's going to stay as it is if we want 150 in there because it's under 255. So we need to change the contents of this register to 150. So the raster interrupts will trigger at line 150. So how are we going to do that? Well, it's simple. We just copy this code and change the value. So we want it to run after it's done whatever it's doing here, which is raster line 0. Oops. Okay, but we want to put 150 in here. So that means the next Raster interrupt, once it's run this, will be at line 150. So it will happen twice now. So it will happen at line 0 the first time. It will hit this. It will change that to 150, and then what will happen is the next when the Raster line hits 0 again, it will do nothing because it's only looking for a Raster interrupt at line 150, and then it will run this IRQ again, which again we do not want to do. We want it to run what's in here when the line is at 150. So how do we do that? Again, simpler than you think. We just change the interrupt execution low and high bits to point at IRQ2. So let's copy that. Paste that into here. I've messed up my tabbing, haven't I? Let's get it all the same. So what we would like to do is we change that to IRQ2. So what we're doing is when we've done our bit in IRQ1, we're changing the raster line that the interrupt occurs at to 150, and we're setting the code that runs to IRQ2, which is all well and good. And then we're returning back to our program, which is down here. Okay, that's all well and good, but all that will mean is it will run this every time the raster line hits 150, and that is all it will do. It will ignore what's in IRQ1 now. So, yet another simple, easy way to do that. What I'd like to do is do exactly the same here that I've done. Let's sort the tabbing out. That I've done in IRQ1. So I'm going to reset this back so that the raster interrupt will occur at line 0. The next one will occur at line 0, and it will run IRQ1. So let's. I know it's quite a lot to take in if you're not sort of au fait with all this. So we've set at the beginning of the program for raster interrupts to occur at line 0 and to run what's in IRQ1. So it runs what's in IRQ1 when it hits 0, and then in IRQ1 we change it so that when it hits line 150, it will run the code in IRQ2. And then when it runs the code in IRQ2, we change it so that the next raster interrupt will occur on line 0 again, and it will run what's in IRQ1. And so it will keep repeating. That's how we've done 2 IRQs. What we have not done is play our music on IRQ2. The reason why we don't do that is because these both will run now every raster redraw. So this will run at line 0, this will run at line 150, and the SID is designed to run once per draw, not twice. So we only include the part of the SID in IRQ1. So, should we see what happens? There we go. So what happens is, we're back in BASIC, but now what we have is a nice tune playing in the background, but we also have 2 borders. So as you can see, this is line 150 here, and the border colour has changed, and it hits line 0 and it changes back to green. So that is the effect of our raster timing there. We can have 2 border colours at the same time. So if you remember from my previous video, I created a sprite on the screen in assembly language. In fact, it was 2 sprites. It was a multi-layered sprite, so it was sprite 1 and sprite 2, and they were overlaid together. Let's include that code in here. Okay, so this is our actual program code. all the rest is interrupt code. So actually, I'll tell a lie. This is our program code. Everything else is run on an interrupt. So what we should be able to do is go to our previous video and copy the code that draws our sprite into here. So I know I've got the start label again, but I'm going to call this sprite just so we can separate it. Again, my tabbing is all over the place, isn't it? So our program will start, it will initialize the music, so it sets the interrupts, initializes the music, then draw a sprite, then return back to basic. Let's save that and run that. Oh dear. Why aren't we seeing anything? Of course we're not going to see anything. We haven't actually copied over our sprite data, which is here, which is stored at memory address 12800. So that's why we ended up with a blank square. So let's just copy this and pop it at the end of our code after our music. So that's telling us we're putting it at this address, and this is our high res sprite and our low res multicolour sprite, and hopefully this is the code here that tells it whereabouts on the screen they are, and we've enabled sprite 1 and 2. So there we go. So we've got a nice multicolour border, and there's our sprite. Right, so how can we use a raster trick on our sprite? Let me show you something. Okay, on IRQ1, okay, before it acknowledges the interrupt, and actually before it changes the raster line, what I'd like to do is load the value 60 into the accumulator. Okay, and I'm going to store that in sprite 0y. Okay, and I also needed to do it as sprite 1y as well, because they're both sprites 1y. Both sprites are turned on, the high res one and the multicolour one, because they're combined to one sprite. So what I'd like to do is I'm positioning the sprite in IRQ1 at line 60. Let's have a look at that. There we go, so it's at the top. So what happens if we, on IRQ2, we relocate the sprite, say to line 170. Well, let's see. Now, yes, so it's just there under where we change the border colour. So let's change that to 170. There we go. So this is what's called sprite multiplexing. We're showing two sprites on the screen, but it's actually well, 4 sprites. We've only enabled 2 sprites, but we're showing 4. It's just showing the same sprite twice, but it's drawing it once when the raster bar is there, and again when the raster bar is there. So it looks like we have twice the amount of sprites on the screen. So what that does is it enables us to show more than 8 sprites on the screen. If we look back on our code, we've only enabled 2 sprites, okay, which is here, these two, and they're both shown one on top of each other, but we're actually showing on the screen, what you see is 4 sprites, Okay, so it's the high res and the multicolor at the top, and the high res and the multicolor of the same sprite at the bottom, so it appears twice. So that is another trick you can use to show more than the defined number of sprites on the screen at the same time, although you'll need some pretty nifty code so you can treat them as separate objects. Okay, so one more thing we can do is another trick that a lot of games use. What we want to do is have a mixture on the screen of two different screen modes. Okay, so we know the Commodore 64 has 4 screen modes, so it's got text or character screen mode basic, which is what you see. It's got text character screen mode multicolor, where you can have, you know, more than one color in a character or a user defined character at the expense of horizontal resolution. And it's got 2 bitmap or high res modes, which is not character based, it's where you actually draw bitmaps. So it's got a high res mode and a multicolor mode of those, and yet again the multicolor mode you sacrifice half the resolution on the horizontal for the colors, and this is obviously due to memory limitations. Normally you can only have one of those modes at any time on the screen. Okay, but we might not want to do that. We might be writing a text-based game where we have high-res graphics as a picture for most of the screen, and then the text description at the bottom. And I know a lot of games do this, not just text adventures. So we're going to use the same trick to do that. Okay, I'm not going to put any graphics on the screen as such, but what I will do is I will just switch modes. So we will use that in IRQ. So once we've drawn our sprite, before we redefine our raster interrupt there, okay, what I'm going to do is I'm going to load the accumulator with this value. It's a hex value. And I will store that in raster line MSB. Okay. Now we've used that for the raster line. This does not affect bit 7. Okay, so if we look at the raster line MSB here, which is D011, and check back to our Commodore memory map, we will see there's some other bits on there, and we've got text mode and bitmap mode and extended background mode on. Okay, so we can use this to switch between bitmap and text mode. There's another address here which does the multicolor mode as well, which is DO16, but for this demo we're not going to do that. So let's go back here. In fact, I've put this code in the wrong place, haven't I? So let's cut that out. I want to do it after the sprites. I put it in the wrong line, so let's put that here. Okay, so when IRQ1 happens at raster line 0, it's going to switch to bitmap mode, or high res mode. Okay, and what we'll do, in fact, should we be really clever and have a third IRQ? Yeah, let's do that. Let's put our standard controls in there for preserving the registers. Okay, oops, didn't want to do that. I want to copy this here, which does the high res. Okay, and I would like to put this value in, which is 1B. Right, so what raster line should we do this at? Okay, so like we did with IRQ 1 and 2, changing the values. Okay, what I'd like to do is maybe do IRQ 3 at line 200. So we're going to tell IRQ 2 when that runs that we want to run IRQ 3 when the raster line hits 200. Okay, so, and then obviously down here we need to, because we're at IRQ 3, we need to set it back so that IRQ 1 runs at raster line 0. And then acknowledge the interrupt. So we've now got 3 IRQs. So IRQ 1 sets the border, puts the sprite at the top of the screen. IRQ 2 at line 170 will move the sprite down and change the border colour. IRQ 3 at line 200 will change the screen mode back to text. I forgot IRQ 1 will set it to bitmap, and IRQ 3 will set it back to text. Let's give this a go and see what mistakes I've made. Oh, I think we have it. So look, when we type on here, we know it's bitmap mode, it's all the way down here, and then we get to line 200 and it's text mode again. See? And it will scroll through. Excellent. Okay, I think that just about covers interrupts. I mean, I may have got a couple of terminologies and numbers wrong, but what have we learnt? Okay, we've learnt how to generate interrupts based on raster positions, okay, and play a SID using that. We've also learnt how we can add multiple interrupts at different raster bar levels, so we can do things like have 2 sprites on the same screen, have 2 different border colours, or we can have 2 different background colours, whatever we want. And we've also learned how to split the screen into 2 different modes simultaneously. Okay, I think that will end the video. So thank you for watching, everybody. And I think what we'll do for the video after this is we will use raster interrupts to do some sprite animation. Okay, thanks again, and I'll see you on the next video.